Howdy gang, welcome back to MAC1140. Today is a good day because we are going to move from our discussion on polynomials and rational functions to a discussion on polynomial and rational inequalities. And I don't think you'll struggle too much with this because it's something that we've actually talked about in the past. It's actually kind of a repeat of material that exists in one of the preliminary sections, section 1.8. And if you have a firm grasp of what's going on with the graphs, specifically as they relate to multiplicities of the factors, then this will make good intuitive sense. I want to begin rather than kind of jumping blindly right into section 3.7. I want to begin with a problem from 3.6. We're going to graph a rational function. Then we're going to use that graph to solve an inequality. Let's see. Sorry, I was just working on something over here. I need to make sure I save it. All right. You guys need this. So this, of course, is MAC1140. That's pre-calculus. Today is a lecture. And it is the 21st of July, 2021. Reminder. Exam 2 is next Monday. Which is 7/26. And you'll have some homeworks and a quiz coming due on that day as well. So where are we here? No, this. You'll have homework 6 and quiz 2 both being due on that day.
Professor.
Yes, ma'am.
I'm finally getting my grant money this week, so what can we talk about, like when I register for the class? I can finally register for the class.
Oh yeah, sure.
I
Sorry.
know I have a lot to make up, but I would rather like be able to put my knowledge into something finally, so I can know if I'm doing it right or not.
Of course, yeah. If you haven't been able to get into WebAssign still, then we need to get you back in and get you working on those missed assignments. Send me an email, Canvas message, or something like that, so we can have a kind of long form discussion. Because I think we'll need to lay out a strategy.
Okay, no problem.
All right. So yeah, exam 2 Monday. The most recent homework is up. I posted homework 6 this morning, and quiz 2 also this morning is are both going to be due on the day of the test. So just like exam 1. Oh, another little announcement. I'm not going to have an office hour today. I'll have my normal office hour again tomorrow, but today my wife and my son both have a doctor's appointment, different sides of town, so I got to bail like as soon as we finish here and start driving them to the places they need to be. So no office hour today. If you wanted to talk about something in office hours today, just like I was saying to Jada, send me a email, Canvas message, and I'll give you a meaningful, thoughtful reply. So just say, hey, I want to come to office hours and talk about this problem, or hey, I want to come to office hours and talk about this section in the book, or whatever, this concept, and I'll give you a good reply. Okay. So we're going to talk today about section 3.7, which is on polynomial and rational inequalities. And these are super important skills to develop for calculus. So in calculus, one of the big things we want to do is find where a function is increasing, where a function is decreasing. But oftentimes, these will be complicated functions that we don't know how to graph. Combinations of polynomials, sines, cosines, tangents, weird rational functions, square roots, all sorts of wild bullshit. stuff that we won't learn how to graph in this class, and that indeed, most people wouldn't know how to graph without some sort of computer assistance. The way you do that is by finding a certain associated function called the derivative, which is intimately connected to that difference quotient, the f of x plus h thing from the beginning of the term. You find this new function called the derivative, and then you solve some inequalities with that derivative. That's what tells you where your original function is increasing or decreasing. There are a few other places in Calc 1 where we care a lot about inequalities like these, but that's the main place. And that increasing decreasing problem is probably the most important problem in the whole first 2/3 of Calc 1. So if you don't have this background skill, then when you get to that portion, even if you're good at the calculus, you're going to run into a brick wall with this algebra skill. So we've talked about it a little bit already. It's introduced in section 1.8. We mentioned this when we talked about finding domains. Today, we're going to look at it in some real detail. I think the best way to do this, though, is to begin with an example from 3.6 and then look at some inequalities. Look at an associated inequality. So this will give us a chance to kind of review the skills that we're supposed to have put together in the previous section, where we're learning how to graph a rational function. And then we'll be able to take that rational function and solve some sort of inequality. Okay. How do we like this one? Is this one okay? I think I'm okay with this one. Sure, what the heck? Yeah, that's pretty okay. So our example here is we're going to sketch the graph of the rational function r of x equals 5x plus 21 divided by x squared plus 10x plus 25. Then solve the inequality r of x is, let's do less than 0. Or how about less than or equal to 0? Okay. We're going to sketch this graph, and then we're going to solve this inequality graphically, which is something we learned how to do, back before the previous test. We will then take that graphic solution to the inequality and try to kind of convert into an algebra procedure. And it's really not too bad. So, kind of pop quiz moment. Who remembers from last time how you get started graphing something like this? I want to sketch this graph. How do you graph a rational function? What were those steps?
Factor.
Yeah, factor.
Excellent. The first step is to factor top and bottom. And the top is a linear polynomial. There's really not any factoring I can do there. But yeah, let's factor. So 5x plus 21. That doesn't need to be factored, but downstairs here factors, right? What is x squared plus 10x plus 25?
Excellent.
I think I heard the beginning from one person and the end from another person. Yeah. So I'm looking for two numbers that add up to positive 10 and multiply to positive 25. That's 5 and 5. So this is 5x plus 21 over x plus 5 times x plus 5, which is x plus 5 quantity squared. All right, this is wonky looking too, isn't it? Yeah, there we go. Okay. I've factored. What else should I be looking for? What was it? We definitely want to find all the intercepts.
Anything that could cross out.
Yeah, so it's true. We would want to look and see if there's anything that cancels here. Are there any common factors top to bottom that we can cancel?
No.
No, right? The top is 5x plus 21, and the bottom is x plus 5 times x plus 5. So there's no common factors there. But that is true. We want to look for that. And if anything canceled, that would tell us maybe there's a hole on the graph. Since we don't have any of that, what would be our next move?
The intercepts.
Yeah, let's find some intercepts. That's fine. Factor intercepts. How do I find the x-intercepts?
And I'm equal to 0.
I heard Erica say set something equal to 0. What was that, Erica? What do we want to set to 0?
Isn't it just whenever y is equal to 0?
Yes, but I don't see any y's here. So what is it that I'm setting to 0 or plugging into 0?
R of x.
X plus 5.
So it's true that x-intercepts come from the whole function being 0. And when we say the whole function, I mean that whole big fraction being 0. For rational functions, there's a kind of quick way to think about it. I'll go through it sort of the long way here. So if my whole function is 0, that means my whole function is 0. And then if I cross multiply by that x plus 5 squared, I just get the top is equal to 0. So remember, if you're trying to find x-intercepts, you can save time by just setting the top equal to 0. Now here, if 5x plus 21 is equal to 0, that means x is negative 21 over 5. Sorry, there's a little coffee stain there. Negative 21 over 5. So the x-intercept, there's only one of them. It's the point, negative 21/5, comma 0. Just for fun, how big is 21/5?
4 1/5.
Yeah, very good, right? 20 over 5 is 4. So 21 over 5 is a little bigger than 4. 4 and 1/5, or 4.2. Negative 4.2 is what we're looking at here. Very good. Okay. Maybe I'll go ahead and say that. It's not even shaky equals. It's actually equals to negative 4.2, comma 0. All right. Y-intercepts. Who remembers how to get these?
Put 0 for in the entire.
Good. Yeah, we're going to plug in x equals 0. Remember, the y-axis is all the points in the plane whose x-coordinate is 0. So when you're looking for the y-intercept, right, the y-axis, all the points in the plane whose x-coordinate is 0, you're looking for the one point where your graph touches that thing. So you're looking for the point on your graph where the x-coordinate is 0. And you're going to plug in 0 for x. So r of 0 here, if I plug in 0 for x, I'll get 21 upstairs. I'll write it out. 5 times 0 plus 21 divided by 0 plus 5 quantity squared. That's 21/25. And about how big is 21/25? Real rough estimate. As rough as you want.
Small.
Small, yeah, smaller than 1, right? 25 over 25 would be 1. 21 over 25 is 4/25 smaller. So it's a little smaller than 1. So the point, your y-intercept here, your x-intercept is this point. Your y-intercept is 0, comma 21/25. Okay, there's two other things we need. Those are the asymptotes. The vertical asymptote, I'll just write VA. The vertical asymptotes, where do we find those?
Do
Bottom equal to 0.
Yeah, I heard it there. We're going to set the bottom equal to 0. one way to think of this is a vertical asymptote is a place where your function is undefined, right? And what sort of fractions are undefined? Well, that's if you try to divide by 0, if you have a 0 downstairs. Another way to think of this, and I think maybe we didn't do this last time, so let me show you really quick. If you take a number and you start dividing it by things closer and closer to 0, like for example, if I divide 1 by 0.1, I get 10. If I divide 1 by 0.01, oh, I get 100. If I divide 1 by 0.001, I get 1,000. So if you divide a kind of normal sized number like 1 by a very, very small number, a number close to 0, those get bigger and bigger and bigger and bigger. So a vertical asymptote is a place where this function is blowing up to infinity, which means it's a place where the top is not close to 0, but the bottom is close to 0. And the actual VA will come from the x value, the location, where the bottom is exactly equal to 0. So we've got x-intercepts, we've got y-intercepts. Vertical asymptote here is what? I said x plus 5 quantity squared equal to 0. So what is x?
Square root of x plus 5.
Oh, well, you could take the square root on both sides, and then you get x plus 5 is equal to the square root of 0. What's the square root of 0?
0.
0. And then if I subtract the 5 over, I get x equals -5. So that's my vertical asymptote. It's the vertical line, x equals -5. Everybody comfy so far? Any questions on these first few steps?
For the intercepts, do we need to express like the intercept in fraction or in decimal? We need
Generally,
to.
I prefer fractions.
Yeah.
You know, I like fractions. I would prefer this and this over something like this. But as long as you're accurate, either one is okay. But you definitely do want to get comfy working with fractions.
Okay.
Before I move on to the last step, does anybody remember the other thing that we kind of get for free when we find the vertical asymptote? Sort of this step where we set the bottom equal to 0, in addition to telling us the vertical asymptote, also tells us something else. Does anybody remember what that other thing is?
The domain.
Yeah, excellent. So we've learned here, in addition to that, that my domain is all real numbers except this guy, right? Everything except for -5. So that's -infinity to -5, union with -5 to infinity. And it's nice to have the domain. So
I have a question about that.
sure.
So if it's everything except 5, would you stop at 4?
No, because
Okay.
-4.5, right? That's a fair question. Fair question. Let's take a look. So here's a number line, and I'll say -5 is right here. I don't want this guy, so I'll put a little circle here. I do want everything to the left and everything to the right of him. So -5 is there, maybe -4 is here and -6 is here. There's lots of stuff in between here. Right, like -4.5 is right here. -4.1 is right here. -4.9 is right here. You know, -5.1, -5.4, -5.9. There's actually infinitely many numbers between -5 and -4, and we don't want to leave those out. So it's a common issue, and I'm really glad you asked that, because I did see a few people making errors of that nature on the test. So when we're saying we're going to kick out -5, that doesn't mean we want to kick out, like we want to stop here. We want to include everything over here. And if you stop at -4, you're missing all of this stuff between -5 and -4. So we really do want to write it like that. It's a different thing, but it's a reasonable question. I'm really glad you asked. All right, one last thing, and it's kind of the complicated thing to figure out. we need the horizontal asymptote. HA. Now here the rule for finding the horizontal asymptote is a little bit more complicated. I can't put it in just a tiny little blue thing like I did for these. Who can remind me the rule for horizontal asymptotes? How do I find these things?
The lead coefficient.
It does. So it's a 3-case rule. And one of the cases involves the lead coefficients. Let's start with that case. So what is the case that involves lead coefficients? When do I look at the lead coefficients? And what do I do with them in that case?
If they the degree is bigger than px is bigger than the degree of qx, there's no horizontal asymptote. If the degree of px is less than degree qx, y equals 0. And then the degree px equals degree qx, it's the ratio of the lead coefficients.
Very good. Yeah, did everybody hear what Ainsley said? So P and Q are the top and bottom, right? So here P of x is this guy and Q of x is this guy. So if the degree of P, the top, if the degree of the top is bigger than the degree of the bottom, then there's no horizontal asymptote. That's the first case in this 3-case rule that we learned last time. If the top has bigger powers of x than the bottom, then there's no horizontal asymptote. On the other hand, if the bottom has bigger powers of x than the top, then the horizontal asymptote is y equals 0. And then that last case, which is the one that I think, was it Erica was saying? If the degree of the top and the degree of the bottom are equal to each other, then we take the ratio of lead coefficients. So the first thing we need to do when we're trying to figure out what our horizontal asymptote is ask what's the degree of the top and what's the degree of the bottom? What's the degree of P and what's the degree of Q? What is the degree of the top?
1,
Very good. There's a linear function. The largest power of x here is x to the 1. What's the degree of the bottom?
2,
2, right? And it's not entirely obvious when you look at it in this form. But remember, if you multiplied this out, this would be x squared plus 10x plus 25. The degree of the bottom here is 2. So in this case, so here, 5x plus 21 over x plus 5 quantity squared. The top is degree 1, the bottom is degree 2. So what does that tell me about the horizontal asymptote?
it's 0.
Very good. And I want you to be very careful about this. It's the line y equals 0.
Okay.
So when we describe vertical asymptotes, we always say it's the line x equals whatever, like here, x equals -5. And when we describe horizontal asymptotes, we want to say it's the line y equals 0, because 0 is a number, but the asymptotes, those are lines, right? It's the line the graph gets closer and closer to. And that's something that the department here at Santa Fe is pretty finicky about, and I therefore must be finicky about it. So we've got all our stuff. Check it out. We factored, nothing canceled, no holes. We found our x and y intercepts. We found our vertical and horizontal asymptotes, and along the way, we got the domain for free.
I have a question about the answer.
Sure.
So let's say we were doing a free response question and we needed to write the vertical and horizontal. Is it okay if we do like HA equals 0 instead of like y equals 0, or?
You could say that the HA is y equals 0, but I need to get the equation of the line. So
Got it.
HA equals 0 would be a point off or something.
Got it.
Sorry, my dot cam decided to turn itself off. Okay. So yeah, we've got all this stuff. And we do want to be careful about the format in which we give the answers. Intercepts, give these as points. Asymptotes, give these as equations of the line. we're ready to draw our graph. So let me purple for our solution. So here's the graph. The way we put this information together into the graph is by kind of just putting in the things that we know for sure. So what do I know for sure? Well, I know that y equals 0 is my horizontal asymptote. So let me draw that in. I'll draw that in as a dotted line. I know that x equals -5 is my vertical asymptote. So I'll draw that in, and you can choose your scales, right? I'll call this -5. And we label those HA, y equals 0, BA, x equals 0. Other stuff I know, intercepts.
Shouldn't x be -5?
Oh, I'm sorry. Yes, yes, sorry, -5. Yes, thank you. Thank you, thank you. Other stuff we know, intercepts. I know that my x-intercept is like -4.2, 0, somewhere around there. So that's going to be right around here. That's my x-intercept. There's only one of them. And I know that my y-intercept was 21/25. So on this scale, that's going to be very small. Right, somewhere over here. All right. This really ain't a lot to go on, is it? We've got these two asymptotes and these 2 points. That graph just from this seems like it could look like anything, right? I don't really know. So the other stuff we want to do is plot some points, right? Plot some points, make a little table. You can just figure out signs if you want. That can be really helpful. So let's go ahead and do that. Let's make a little table. And for some values here, I might try to figure out exact values. For others, I might just try to figure out the sign. -5 is obviously out, but we could try something like -6. Try something like 1. Let's just start with these and see how we feel about what we get. So remember, r of x here, my function is 5x plus 21 over x plus 5 quantity squared. So if I plug -6 into this function, the top is going to be 5 times -6, which is -30 plus 21. So the top there is -9. And the bottom is going to be what? Well, that's 6 plus 5 is 11 all squared, which is 121. In particular, it's negative, right? And that's sort of what we care about most. So that tells me that over here, just to the left of -5, 9 over 121, that's very small, right? The denominator there is much bigger than the numerator. So I've got a point, somewhere over here. And in particular, it's negative. That's what I want to emphasize. If you plug in something like +1, you get 5 plus 21 is 26, divided by 5 plus 1 is 6 squared is 36. 26 over 36 is smaller than 1, but positive. Something like this. And believe it or not, that's enough for me to fill in the rest of the graph. Look over here. What do you not have to the left of 5? I've got one of them here, but I don't have any of them over here.
Oh, x-intercepts.
Yeah. So if my function is negative right here, this is 6. If the y value for my function is negative when x is equal to -6, and there are no x-intercepts anywhere over here, what can you say about the function everywhere over here?
Negative.
It's got to be negative. In order for that function to be positive anywhere over there, it would have to cross the x-axis. So that means two things. It means that I'm going to be sneaking up on this horizontal asymptote from underneath, not from above. And it means I'm going to be blowing up at this vertical asymptote going in the downward direction rather than in the upward direction. So my graph's got to look something like this over here. Okay. This vertical asymptote is coming from a factor of the denominator. Remember, the vertical asymptotes come from the bottom being 0. What's the multiplicity of the factor that gave that vertical asymptote?
2.
2, right? X plus 5 all squared. Multiplicity 2. So is my arrow on the right-hand side of this asymptote going to be pointing down or pointing up, and why?
Up because it's a different, oh wait, would it be the same because it's even?
Very good. Very good. Did everybody hear what Ainsley just said? When you jump over a graph feature that comes from an even multiplicity factor, the sign doesn't change. This vertical asymptote comes from this factor, which is an even multiplicity factor. Therefore, because I'm negative on the left of it, I will be negative on the right of it. In other words, the arrow points down on both sides. If this was an x plus 5 cubed, then I would know that the arrow on the right side would be up here, pointing up, because that would be an odd multiplicity factor. But since this VA comes from this even multiplicity factor, I know that it's got to have the same sign on both sides. I want to take a second to really digest that. Does anybody have any questions about how I know this arrow points down? It's going to be important for inequalities. Okay. If I wasn't sure, I could try to plug some x values in. But I've got this x-intercept right here, and this x-intercept is so close to this vertical asymptote, I would have to find an x value that's between those to plug in order to detect that this arrow points down, in order to know that this function is negative there. Now, in addition to that, let's think about this guy. This x-intercept comes from the top, right? X-intercepts for rational functions come from the top being 0, factors of the top. What is the multiplicity of the factor that gives us this x-intercept?
1.
Very good. Just like Erica said there, the top here, 5x plus 21, that's the only factor upstairs, is a multiplicity 1 factor. It's 5x plus 21 to the 1. So are we going to change sign, or are we going to stay the same sign? Are we going to cross the x-axis there, or are we going to like bounce off of it?
Cross.
We're going to cross because it's an odd multiplicity factor. You could also deduce that from the y-intercept being positive, right? My function can't stay negative over here and have a positive y-intercept. It's got to become positive. So I know here we're going to cross. Alrighty, well, let's draw in that portion of the graph. I've got something like this going on. And we have to hit that y-intercept. And then we have to sneak up on this asymptote. And I know I'm going to be sneaking up on it from above because, again, there's no x-intercepts over here. This point, remember, is 1, 2636. So my graph, I'll try to draw it smooth. Has to look like this. Is it perfect? No. Is it pretty good? Yeah. Does it nail all the important features? Yes. Just like when we were drawing those graphs of polynomials, right? We said the graphs weren't perfect, but when we flipped back and forth from Desmos to the graph, it was really close. Let's take a look. Let's see how we did. So this is the graph y equals r of x. Over here, this is my x-axis. Let's label these points. So the point right here was -6, -9/121. The point right here was what was our -21/5, 0. The y-intercept right here was 0, 21/25. And I did even have one extra point here. I can plot that. That's 1,26/36. So these are weird numbers, right? You wouldn't guess these, even if you were looking at a graphing calculator, you wouldn't guess these correctly. You gotta do the algebra. Now I claim this is a pretty good graph. Let's see what Desmos says. Whoa, not bad. Not bad at all. If I do say so myself. All right. So we can draw good graphs of rational functions, even weird rational functions, by going through this process. You find asymptotes, intercepts, and then if you're still unsure, which is certainly the case here, we weren't sure, make a little table, plot just a few points. You don't need many. That's it. That's the game. So a graph is done. Remember the other thing we said we wanted to do? Let's solve the inequality. R of x is, what do we say, less than or equal to 0. Which is the same thing as saying 5x plus 21 over x squared plus 10x plus 25 is less than or equal to 0. That was the other task we set for ourselves. We're going to do it graphically, but I'll go ahead and write the factored form here too. 5x plus 21 over x plus 5 quantity squared is less than or equal to 0. It's going to help us. Help us think about this stuff in a smart way. Graphically, how do I solve this inequality using this graph? What am I looking for on the graph when I say I'm trying to find the solution to this inequality?
Are you trying to find the solutions?
Yep. Yeah, I'm trying to find the solution to the inequality. R of x is less than or equal to 0. So what does that even mean?
The things below 0, like the
Or
point.
the
The
domain.
solutions below 0?
Yeah, I think I heard the critical things there from a few folks. I'm looking for all the places where the y value is below or less than 0. So on the graph, what is that? Kind of in terms of the picture here.
Everything below the x-axis.
Yes, very good. I'm looking for the parts of the graph that are below the x-axis. So that's these parts, right? Everything up to here. Okay, let's think about it a little bit carefully. Graphically, we're looking for where is the graph beneath the x-axis. Right? Remember the xy plane is all ordered pairs, x comma y. I'm looking for the parts of the graph where the y values, which is r of x, right? This is the graph y equals r of x. Looking for the part where the y values are less than 0. That means I'm looking for the pieces of the graph which are beneath the x-axis, because everywhere beneath the x-axis in the xy plane, the y values are less than 0. What does this word where mean in mathematics when we say where is this function something something? Remember what was the vocab trick there?
Okay.
Right, it's the location. And what do we mean when we say where, or when we talk about locations? Think back to our lecture on mins and maxes. What do we mean by that?
Is that the x value?
Right. Where does something happen on a graph is always the x value. So what we're looking for is for what x values is the graph beneath the x-axis. So your solution to this inequality is going to be a set of x values such that at those x values, the graph is beneath the x-axis. Is 0 going to be a part of our solution? Is x equals 0 going to be in our solution set?
No.
No, very good. X equals 0. Here's the point on the graph where x is equal to 0. We're not beneath the x-axis there. 1 is not a part of our solution. Here's the point on the graph where x is equal to 1. That's not beneath the x-axis. Is -6 going to be a part of our solution set?
Yes.
Yes, it is, right? Here's the point on the graph where x is equal to -6, and that point is beneath the x-axis. What about -5? Is -5 going to be a part of my solution set?
No.
Good. Why?
Because the graph never reaches it.
I like Ben's answer there. Benjamin said the graph never reaches x equals -5. In other words, there is no point on the graph whose x coordinate is -5, right? Nowhere along this blue dotted line is there a point on the graph. The graph dives down here and the graph dives down here, but there is no point right on that line. Okay, let's be a little bit more careful about it then. We know that the part of the function that satisfies this, the part of the graph that satisfies this condition is this stuff. So what are the x values for this whole chunk of the graph?
It'd be parentheses, negative infinity, comma, -6 bracket, union. And the last part I got, I know it's -21/5, but I don't know what's after that.
Okay, let's back up for just a second. What about between -6 and -5? Are these x values a part of our solution set? Like -5.5, -5.8?
Yeah, they are.
Yeah, those would be too. So we don't want to stop right at -6. We want to include everything on this part too. So this would be the set -infinity all the way out here up to -5. So that's all of this part of the graph. Union with this part of the graph, right? Everything, so from -infinity all the way up to -5, the graph is beneath the x-axis. At -5, the graph doesn't exist. There's nothing there. But then from -5 all the way up to -21/5, the graph is beneath the x-axis again. So union that with -5 to -21/5. And this is your solution.
Wouldn't it be a bracket at the -21?
Oh shit, yeah, we're solving less than or equal to. Thank you.
Yeah.
Bracket here. Very good, very good. Bracket on the right, yes. What about at -5? Brackets there?
Nope.
No, right? Because the function isn't defined at -5. Okay, excellent. We solved the inequality. Wouldn't it be nice if we could do that without going through all the bullshit of drawing this graph? Drawing this graph took a long time. Well, what do you notice about the numbers that show up here? They're all associated with important features of the graph. -5 shows up in our solution set in two places. -21/5 shows up in our solution set. All of those numbers are numbers that we at some point calculated or discovered before drawing the graph when we were finding vertical asymptotes and x-intercepts. Turns out that's the key. Turns out that's the key. So I'm going to move away from this in a second. Are there any questions about how we got the graph or how we got the solution to the inequality?
Do you have to always graph it to find the solution?
Nope. What we're going to do next is see how to get the inequality without the graph. That's going to be the game. So there's kind of two big things going on. One of them is a theorem. But before I go back over that theorem, right underneath this graph, I'm going to draw just the x-axis. And on this x-axis, I'm going to plot just the kind of important numbers from our function. Those were -5 and put it here, -21/5. All right, -5, that was where our function is undefined, the vertical asymptote, and -21/5, that was where our function is equal to 0, the x-intercept. If I use those numbers to chop up the x-axis, you'll see my function is negative everywhere over here. Everywhere to the left of -5, my function is negative. Everywhere between -5 and -21/5, my function is negative. That's this piece right here. And then everywhere to the right of -21/5, my function is positive. You can come up with this number line without ever drawing the graph by first finding the -5 and the -21/5 and then making a little table. Not even the full table, just the signs. So right away, this tells me that r of x is negative on, I'm doing strictly negative here, on -∞ to -5, union with -5 to -21/5. And r of x is positive, strictly positive, on the interval -21/5 to infinity. Right? Even without the graph, if you have this number line, you can solve those inequalities. Easy. Just where do we have a minus? Where are we negative? Well, -∞ to -5, -5 to -21/5. Boom. Where do I have a plus? Where is r of x positive? From -21/5 to infinity. Boom. So the goal for us is going to be to get this number line without drawing the graph. And the trick is going to be find the numbers that go on the number line, which are the places where your function can change sign. Places where it's possible for your function to go from negative to positive or from positive to negative. That can happen in two ways. Either your function crosses the x-axis or has a vertical asymptote. If your function is otherwise continuous, and this is the theorem, so here we go. Only if one of two things is true. One, x equals c is a root, aka 0, aka x-intercept, or x equals c is a vertical asymptote. This is a consequence of the intermediate value theorem. You guys remember that? We said if f of a is negative and f of b is positive, then somewhere in between there's a c such that f of c is 0. This is kind of a converse to that, kind of a we call contrapositive to that, saying that, you know, if you're negative on one side, positive on the other, you had to cross 0. In other words, the only way to go from negative to positive is to cross 0. That was for continuous functions. Now, rational functions are not continuous everywhere. They're discontinuous at their vertical asymptotes. So for a rational function, and that includes polynomials, by the way, every polynomial is a special rational function, just with downstairs q of x being the constant polynomial 1. A rational function can change sign only at x-intercepts and vertical asymptotes. So if you want to come up with this number line, you need to find the places where you can change sign. That means you need to find x-intercepts and vertical asymptotes. Then you test a point from each of these 3 regions, or from each of the however many regions. If you're negative anywhere in here, you're negative everywhere in here. If you're negative anywhere in here, you're negative everywhere in here. And if you're negative or positive, whatever, over here, at any point, you're negative or positive, whatever, everywhere over there. What's more is that the multiplicity trick will allow you to save time. Imagine I've drawn that number line, but I haven't filled in the minuses and the pluses yet. Then I look at my table and I go, oh, well, when x is equal to -6, the function is negative. That would mean I can put a negative over here, right? -6 is like right here. When x is -6, my function is negative, which means it's got to be negative everywhere in this region. Now, I know that the -5 on my number line came from a multiplicity 2 factor, x plus 5 squared, which means I'm not going to change sign as I jump over that guy. I don't go from negative to positive, I stay negative. We don't change sign when we jump over features that come from even multiplicity factors. So we get this guy from our table. I get this guy by saying, oh, I have to stay the same sign because even multiplicity. This guy came from an odd multiplicity factor, so I know I got to change signs. So since I'm negative here, I got to be positive here. That's how quickly you can fill this shit out. So let's try this with something a little more complicated looking. Grab us a fun example to play with. Okay, this time I'm going to use a polynomial. Remember, polynomials are rational functions. They're just especially simple rational functions. We're not going to draw the graph. Just going to solve by leaning on this theorem. I'm going to solve the inequality 2x cubed plus x squared plus 6 is greater than or equal to 13x. I'm going to give you steps for this in a minute. I'm going to kind of just write down step 1, step 2, step 3. But for now, I want you to think along with me. My goal is to use the same thing we just discussed. I'm going to draw a number line and then test a point from one of those regions and then use my multiplicity trick to deduce the sign in all the other regions. In order to do that, I need to have like an inequality that is of the form we're playing with, like f of x is greater than 0 or f of x is less than 0. It's got to be like this. One side needs to be 0. So the very first thing we should do is pull this 13x from the right over to the left. Like I said, I'll outline steps in a minute. The first step is going to be pull everything to one side. I'm going to write the minus 13x, then the plus 6, so that it's in the kind of normal order. So now I've got an inequality of the form, some function is greater than 0. Greater than or equal to, that doesn't matter. Some shit is greater than or equal to 0. Got to make one side 0. Next, I need to go hunting for these points, places where my function can change sign. can change sign at roots, can change sign at vertical asymptotes. Does this apparatus have any vertical asymptotes? Two x cubed plus x squared minus 13x plus 6. Is it possible for this thing to have vertical asymptotes?
No,
Good. Why?
there's no bottom to the set it equal to.
Perfect. Everybody hear what Erica said? There's no bottom, right? The downstairs here, there isn't anything downstairs that could be 0. So there's no vertical asymptotes. Is it possible that this thing has any roots or x-intercepts?
Yes.
Yeah, it's a polynomial. How do we find the roots of a polynomial?
The exponents.
Um,
Well, when you graphed it, I mean, you would solve,
I
but
see what you're thinking. Yeah, you're looking at multiplicities, right? Think back just a little before then, though. Think back to the section day before yesterday. How do
factor.
we find- yeah, we factor it. Very, very good. We got to factor. So our goal now is to factor this thing. That can be a bit of work, right? This is a degree 3 polynomial. I don't see any obvious way to factor it by grouping. So what we're going to do to factor this is use our rational roots theorem. They're of the form P of plus or minus P over Q. So we got to come up with our P's, come up with our Q's. Remember, the P's are divisors of the constant term. So that's 6, 3, 2, and 1. Q's are divisors of the lead coefficient. Those are just 2 and 1. So our possible rational roots are plus minus P over Q stuff. This could be 6 over 2 plus minus 6 over 2 plus minus 3 over 2 plus minus 2 over 2 plus minus 1 over 2 plus minus 6 over 1 plus minus 3 over 1 plus minus 2 over 1 and plus minus 1 over 1. So our goal here, what we're trying to do is we're trying to factor. We pull everything to one side and then factor. I'd have to check all of these. Now there might be some repeats here, like 6 over 2 is 3, so it's plus minus 3, plus minus 3 halves, plus minus 1, plus minus 1 half, plus minus 6. 3 we've already got, plus minus 2, plus minus 1. So I've got 1, 2, 3, 4, 5, 6, 7, 14 total possible rational roots that I would have to check. I'll tell you, I've done this ahead of time, so rather than checking one at a time, let's test 2. So I want to know, is 2 a root? And if so, how does that help me factor this? So I write the suspected root and then the coefficients. That's 2, 1, negative 13, 6. And I do the synthetic division. Bring down the 2. 2 times 2 is 4. Add those up. 4 plus 1 is 5. 2 times 5 is 10. Add those up. That's negative 3. 2 times negative 3 is negative 6. Add those up. That's 0. So yay. The remainder is 0, which means 2 is a root, which means x minus 2 is a factor. And the quotient, when we factor out the x minus 2, what's left is 2x squared plus, 2x squared plus 5x minus 3. Okay, and we're not done factoring yet. We got to finish factoring this quadratic over here, and that requires the AC method. So here's us kind of getting started factoring. And now if I want to factor this guy, I have to find 2 numbers that multiply to a times c. So a little divider here, ac here. 2 times negative 3 is negative 6. What I'm trying to do is factor 2x squared plus 5x minus 3. So 2 numbers that multiply to negative 6 and sum to positive 5 would be, let's see, positive 6 and negative 1. So I rewrite 2x squared plus 5x as plus 6x minus 1x minus 3. And then I factor by grouping. So that's 2x times x plus 3 minus 1 times x plus 3, or 2x minus 1 times x plus 3. So now we're done factoring. I've got x minus 2 times 2x minus 1 times x plus 3 is greater than or equal to 0. All right. So no VAs. Roots and x-intercepts are x equals 2 from this first factor, 1/2 from the second factor, and -3 from this third factor, all of multiplicity 1. Plot those on a number line. So -3, I'll put here, 1/2, I'll put here, 2, I'll put here. That's going to split my number line into 3 regions. And in each of those regions, my polynomial here is either positive, which would mean we're solving that inequality in that region, or negative, meaning we're not solving the inequality in that region. And for polynomials, there's an even faster way. You don't even need to test any points. What's the end behavior of this polynomial?
As x goes to infinity, y goes to infinity.
And as x goes to negative infinity?
It goes to negative infinity.
Good. Odd degree, positive lead coefficient. So as x runs off to the left, over here in this region, I know that this function is negative. Negative. That's by end behavior. Or you could test some number like x equals -4. I'm not going to do that, but you could plug -4 into this thing and see what you get. But by end behavior, I know that this polynomial is negative for very large negative x values, which means everywhere in this region, it's got to be negative. Plus or minus goes here. Which one?
Positive.
Good, plus, yeah, positive. Because this feature, the root at -3 is an odd multiplicity root. Every single one of these is multiplicity 1. So we're going to change sign as we jump over this. The 1/2 came from this multiplicity 1 factor. So since I'm positive here, I'm going to change sign as I jump over that. The 2 here comes from this multiplicity 1 factor. So I'm going to change sign as I jump over that. That's it, guys. We're done. We just got our number line. We didn't
Wait.
have to draw the graph.
Can you explain that again? I kind of got lost.
So
Like-
let's look at the graph real quick. This is x minus 2, x 2x minus 1, and x plus 3. Here's the graph of this function. At every one of these x-intercepts, at every one of these x-intercepts, my function is going to change sign. It's going to cross the x-axis because they're all coming from odd multiplicity factors. So for example, the x-intercept over here at -3, I know from the end behavior of this polynomial that to the left of -3, the function will be negative. Because I know when you go way, way out here, and the arrow points down, right? The graph goes down as you go off to the left. That's the end behavior. So I know that I'm negative in this region. And then the question is, if I know that I'm negative in this region, can I say whether I'm negative or positive in this region? To answer that, we ask, well, okay, the thing that divides one region from the other is this guy, -3. This guy. This guy is a multiplicity 1 root, or he comes from this multiplicity 1 factor. Because the
Oh.
multiplicity of the factor is odd, we're guaranteed to change sign as you go over it. Remember we talked about the behavior near roots? If this was like a multiplicity 2 root, then we would bounce off. If it was
Yeah,
a
I get it now.
multiplicity 2 root, we would have like an S-shaped squiggle, but we would still cross. So every one of these factors, odd multiplicity, which means every one of these jumps we take, we're going to change sign, plus, minus, plus, minus. So
Okay,
once you
got
know
it.
what happens in one region, you know what happens in all the regions. So now you just write down your answer. Where is this thing greater than or equal to 0? Well, that's the regions with the pluses. So -3 to 1/2 union with 2 to infinity. We want to put the parentheses or brackets in correctly. This guy, we're asking where is this greater than or equal to 0? And each of these were equal to 0, so we'll include those. Those are okay. If it was a strict inequality, just strictly greater than, we would use parens everywhere. That's it. By far the hardest part was factoring, right? Getting from the start to here. All this work was just to get the polynomial factored. So if I give you the thing factored, life is good. Life is easy. You can solve this really quick. If I don't give you the thing factored, you got to pull everything to one side and factor before doing this. Let me go ahead and outline the steps and then we'll work one more. Before I move away and write down the steps, are there any questions, any other questions on what we've done here?
So would the final answer be
Question.
the number line, or would we have to, since we're solving, do we need to write out like the,
Yeah,
okay.
we want the interval notation usually. So this would be our final answer. Any other questions?
To the side where you did A times C equals -6. Why did you do that?
So I'm trying to factor this quadratic. So in here, I'm trying to factor the quadratic that was left over after I pulled out my x minus 2 using synthetic division. So I'm trying to factor 2x squared plus 5x minus 3. So this is that AC method for factoring quadratics. And we needed to use that, or we wanted to use that there. The synthetic division took me from here with this degree 3 thing totally unfactored to here. So by making a list of possible rational roots and finding one that worked, I was able to say, okay, this big scary polynomial is equal to x minus 2 times 2x squared plus 5x minus 3. The x minus 2 is this, 2x squared plus 5x minus 3 comes from this. So that synthetic division gets me from here to here. But in order to solve the problem, I need to completely factor the polynomial. And that's not done until I've broken this quadratic up into his factors. So to go from here to here, I used the AC method down here to factor. So in other words, remember the AC method says multiply A and C, and then look for two numbers that multiply to that and add up to B. So I needed to find two numbers that multiply to -6 and add up to +5. I used +6 and -1. Then you rewrite the middle term. So I rewrite 2x squared plus 5x minus 3 as 2x squared plus 6x minus x minus 3, and then factor by grouping. Once we get that, these guys, we know that quadratic 2x squared plus 5x minus 3 is equal to 2x minus 1 times x plus 3. So that's how I go from here down to here. And once I have this, I'm golden. So take your time.
Okay,
Maybe
thank
Anna,
you.
take your notes if you want to. If there's other little things you want to write in there, take a second to make sure it's in a way you could look back at it and get something out of it. Other questions on this one? Okay, here come the steps. Steps for solving polynomial and rational inequalities. First thing we had to do, pull everything to one side. Make the other, which in other words, what we're doing is make the other side 0. So remember where we started with that last one. We started with 2x cubed plus x squared plus 6 is greater than or equal to 13x. And to pull that 13x over. Then factor everything. Oh, and if your function, if it's a rational function, you may need to have a common denominator. Right? So pull everything to one side, common denominator. If necessary. Right? If there are denominators, then you'll need to put it all into one fraction, the common denominator. Then factor everything. Factor the top, factor the bottom. If it's just a polynomial, there's no bottom. Then you write down the roots, x-intercepts, whatever you want to call them, and vertical asymptotes. You put those on a number line. And then finally, you fill out the signs. How do we want to say this? Determine the sign, the SIGN sign in each region on the number line. And this can be done a bunch of different ways. This can be done if you're stuck using test points in each region. You can use multiplicities. And you can also use end behavior. You can use the horizontal asymptote or end behavior. So in our last example, we used the end behavior of the polynomial to say in the leftmost region, the function had to be negative. And then we used multiplicities to jump over each of the little dividers. If your function is a rational function and that horizontal asymptote is not 0, let's say the horizontal asymptote is 5, then you know when you go way off to the left, the y values on the graph get really close to 5. In particular, they got to be positive. So that would tell me that my leftmost region is positive, and then I could use multiplicities to hop over each of the things. But if you get stuck, or if you're not sure, if you want to double check, you can always test a point from each region. Okay, we have finite time here, so let's do another example. What are we doing? Oh, we're doing okay. All right. Where's a nice problem? Everybody got these steps written down? Okay. So, example. I want to solve the inequality x squared minus 4x plus 3 divided by x to the 4 minus 4x cubed minus 5x squared is greater than or equal to 0. Here, everything has already been pulled to one side and put together with a common denominator. Don't need to do any of that, which is nice because those steps can take a while. So
Is
looking
that a 4x to the third
yes,
power?
yeah,
Okay.
4x cubed, 4x to the third. This is a 5x squared. All right. So everything is already on one side. Everything's already put together in a common denominator. What's the first thing I should do?
Factor.
Very good. So the top, x squared minus 4x plus 3. I'm looking for two numbers that multiply to 3 and add to -4. That would be x minus 3 times x minus 1. The bottom, each of these terms has an x squared, so I can factor out x squared, and what's left is x squared minus 4x minus 5. And now that x squared minus 4x minus 5, I can factor that further. So this is x minus 3 times x minus 1 all over x squared times two numbers that multiply to -5 and sum to -4. Oh, that would be -5 and +1. So this is x minus 5 times x plus 1.
Wait, how did you get rid of the x squared? Did you bring it down?
I haven't gotten rid of it. I factored it out.
Oh yeah, I'm
So
sorry.
each of
Okay,
these-
never mind.
That's all right. Yeah, each of these, the x to the 4x cubed x squared, can give an x squared. So I factor that out, and that guy goes right here. Right here. So what are my kind of special numbers, places where I can change sign? What are my roots and x-intercepts?
You can say that x cannot equal 0, 5, and -1.
That's true, right? If we're talking about the domain, we can't have any of these factors down here being 0. But remember what we're looking for. We're looking for roots and x-intercepts. Sorry, roots, aka x-intercepts, and vertical asymptotes. So those numbers, in addition to not being in the domain, they're important to the process. 0, 5, and -1 are all vertical asymptotes. This function. So x equals 0, 5, and -1. This function would have 3 vertical asymptotes, which are all places where sign changes can happen. And the other place are roots, x-intercepts. What are those?
Positive x plus 3. I mean, x equals 3 and x equals 1.
Yeah, good, good. Setting each of these to 0 on their own, we get x equals 1 and 3. So those are what go on my number line. Lots of stuff here. I'm going to make the number line nice and big. Can't answer that right now. -1. It's important you put these in order. It might sound silly, but if you put these on the number line in the wrong order, then the trick doesn't work. The multiplicity thing doesn't work. So pay attention to that. -1 is the leftmost of all these numbers on my number line, then 0, then 1, then 3, and then 5. Kind of ran out of space there. So I take all those numbers, I put them on my number line. And now I need to fill out the signs. Unfortunately, this rational function, his horizontal asymptote, his end behavior is y equals 0. And that doesn't tell me whether we're positive or negative at either of these endpoints, right? If this guy had horizontal asymptote y equals 5, then I could say, oh shit, we got to be positive over here. We got to be positive over here, because that means the y values get close to 5 as we go far away from the origin. So we do need to test a point here, but we only need to test one point. So I'll come over here and test x equals -2. If I plug -2 into this apparatus, I get -2 minus 3 times -2 minus 1 over -2 squared times -2 minus 5 times -2 plus 1. And I only care about whether we're positive or negative, but just to be, thorough or whatever, that's -5 times -3 divided by +4 times -7 times -1. So what is that? That's +15 divided by -7 times -1. +7, 7 times 4 is 28. So in this leftmost region, the region under which I've written test x equal -2, is this function here positive or negative?
Positive.
Positive, right? Because if we're positive when x is -2, we're positive everywhere in this region. So plus here. All right. What about the next region over, the region from -1 to 0?
Negative,
Good. How do we know? How do we know?
because
we don't say-
multiplicity is 1.
Good. This guy, the -1, that root, or sorry, that vertical asymptote is coming from this factor, which is a multiplicity 1 factor. So we will change sign. What about from 0 to 1? Do we stay negative or are we going back to positive?
Negative,
Positive.
So the negative was correct. We're negative in this region, we know that. What's the multiplicity of the factor from which this guy comes?
2.
Good. The 0 on my number line is coming from this factor, right? That's where we got him. This factor. And that's a multiplicity 2 factor. So if it's an even multiplicity, you don't change sign. If it's an odd multiplicity, you do change sign. So we change sign here because that came from an odd multiplicity thing. We go from positive to negative. We don't change sign here because that comes from this even multiplicity thing. So negative stays negative. What about as I jump over +1?
Positive,
Good. The +1 is coming from this factor, which is again a multiplicity 1 factor. So we change sign there. As we jump over 3, what about between 3 and 5? Positive or negative?
Negative.
Negative. The 3
Negative.
yeah, excellent. The 3, this guy, is coming from this factor. This factor is, again, multiplicity 1. So we do change sign. And then finally, as we hop over the 5, that's coming from this factor downstairs. That's also multiplicity 1, so we do change sign there. All right. I wouldn't want to graph this function. It's not going to be a simple thing. But this ain't hard. So my solution is going to involve which regions? Well, I'm asking where is this function greater than or equal to 0? So I'm interested in places where the graph is above the x-axis, where the function is positive. So that's going to be this region, and this region. So that's from -infinity up to -1. I'm going to leave off the bracket or paren for now. From 1 to 3. There. And from 5 to +infinity. Now we need to figure out for each of those endpoints, do we use a paren or a bracket? If this is a strictly greater than or strictly less than, it'll all be parens. But here it's a greater than or equal to. So I need to figure out paren or bracket, paren or bracket, paren or bracket, and paren or bracket. Is -1 a part of my solution set or not? Do I use a paren or a bracket on -1?
Bracket.
Parentheses,
Parentheses.
parentheses, because it's a
Parentheses, correct.
vertical asymptote.
Good. If you plug -1 into this, you don't get 0. You get something undefined. The bottom is 0, right? This factor. So -1 can't be a part of the solution set to this inequality because the inequality is undefined when you plug -1 in. So he gets a paren. What about +1? Paren or bracket?
Bracket.
Excellent. +1 gets a bracket. Because if you plug +1 into this inequality, the top is 0, the bottom isn't 0, the top is 0. So 0 over something else, that's 0. So if you plug 1 in here, you get the statement 0 is greater than or equal to 0. So Jada says we use a bracket there, and that's perfect. What about the 3? Paren or bracket?
Bracket.
Bracket again, same reason, right? The x minus 3 factor is upstairs. So when he's equal to 0, this thing is okay. 0 is greater than or equal to 0. That's a true statement. So we include 3. What about the 5?
Parentheses.
Paren, because the x minus 5 factor is downstairs. 5 makes that thing undefined. So that's it. Game done. Not too bad, right? Hell of a lot easier than trying to graph this nightmare complicated rational function. I have no idea what that graph looks like. I know it's got vertical asymptotes at 0, 5, and -1. I know it's got the x-intercepts at 1 and 3. But I don't want to take the time to try and draw that graph. I guarantee you it's quite complicated. This is how you solve inequalities. That's it, gang. That's it. That's the whole section. We're about 5 minutes early here, but I do have to rush my wife to her doctor's appointment. And we did just cover exactly what I wanted to cover for today. So I'll take a second to field any questions. Is there anything that that you guys want to ask about, talk about before I let you go? Questions on this example or any of the earlier ones? Okay, you have a new quiz and a new homework up. Those went up this morning and they're both due on Monday, which is the day of our test. Remember, test on Monday, quiz and homework due then. I cleared out all the extension requests that were there. So if you submitted an extension request yesterday, day before, whatever, it's been cleared. Please knock that shit out. If you need an extension on any of the older homeworks, please submit those requests ASAP. I'll clear them again one more time today because I want you working on this shit between now and the test. Remember to work hard. And remember, I'm going to write this down, put it in your notes. Draw the damn graphs by hand when working homework and quiz. All right, do it. Do it. And by that, I don't mean like guess until you get the right one, then draw the graph on your paper. I mean, go through the procedure that I've been going through in class to draw the graph, then match WebAssign's graph to yours. Draw your graph first. Don't cheat yourself on this shit. A big part of the second exam, the exam on Monday, is going to be you graphing polynomials, you graphing rational functions. So you need to practice this stuff. Especially important is the local behavior near the roots, the cross versus the bounce, right? And this multiplicity trick, all of that stuff to do with factoring and multiplicities is going to be huge on the test. You must get good at that. And the best way to get good at that, the best way to start making sense of this is to practice drawing the damn graphs by hand. So please do that. I beg of you, please do that. If you're unsure, you want to check a graph, use Desmos. If you're having trouble with something, you're like, I'm not getting what I want to, take a picture, send it to me. I'll reply to you quickly. Please practice that skill. You're going to need it on the test.
For the quiz, would you say that's like a good study habit to like practice the quiz a couple times? Like that's a good study tool?
I would say make sure you do the homework first. do the homework first, but then once you're done with the homework, if you run through the quiz and you're like, yeah, these are easy, I'm nailing this shit, then you're in good shape. If you feel like the quiz is hard, then the exam will probably be hard. I'm not sure that repeating the quiz problems is all that helpful, right? Once you've solved a problem once, kind of all the mental stuff is done and you're just like grinding. So I'm not sure how much repetition of the same problem is valuable, but solving similar problems is really good. So if there's a particular problem from the quiz that gives you a hard time, I would say go look for other problems like that. You can message me and say, hey, can I have other problems like this to practice? That would be really good. So at a base level, yes, making sure you can solve the quiz problems is a good study habit, but solving and resolving the exact same problem over and over again might not be as helpful as solving new but similar ones. Any other questions? Alrighty then, no office hour today. Remember, I'll be a little bit busy, but if you want to talk, send an email or something like that. Work hard on the homework and the quizzes. If you need help, reach out to me, please. And that is it. I'll see you guys tomorrow.
Bye.
Bye, guys.